Hello, in this video I'd like to talk about fictitious forces in a rotating system, specifically discussing the centrifugal force and the Coriolis force. In our first discussion of fictitious forces, we took two systems, one which was at rest and the other which, relative to our first system, was moving with an acceleration of a on a straight line, in this case across the x-axis, relative to our first system. Now in this example, we again have two systems where one is at rest and the other is in relative motion. So our first system, the system in black, xy, is our system at rest. That's where our laboratory is, where we take measurements. The red system is rotating around the black system and they share the same origin point. So standing on the same point where the laboratory is, we can imagine there's a ballerina. And this ballerina is rotating with an angular velocity in a counterclockwise direction. So let's imagine again that the ballerina and the laboratory are at the exact same point. They share an origin. And the angle between the x-axis of the ballerina, that is x tag, and the x-axis of the laboratory, that is x, is the angle theta. Well, that means that the integral of theta dot, equals omega. And this omega, or theta dot, represents the change in the angle over time. We can also call this the angular velocity. In a case like this, where we have one system that's stationary and another rotating around it, and they share an origin, we consider the rotating system to be a non-inertial system. And that means that we have to account for fictitious forces in this rotating system. And so if we were to measure an object, say this triangle in blue, from the perspective of both the ballerina and the laboratory, we would get two different measurements. And to account for these different measurements, we would need to add fictitious forces to our system to make Newton's second law applicable. Keep in mind this is only the case if one of the observers is rotating. If this triangle were to rotate around the laboratory, it would not mean we need to add fictitious forces, and we would not need to account for the centrifugal force or the Coriolis force. Only when one of the observers, in this case the ballerina, is rotating, do we have to add the fictitious forces of the centrifugal force and the Coriolis force to make Newton's second law work. So let's get down to brass tacks and talk about the actual forces we're measuring. So first let's assume this blue triangle is moving with a velocity v in a direction more or less parallel to the x-axis. If that's measured from the origin by the laboratory, by the stationary system, we'll get a measurement of v. However, if we're measuring from the perspective of the spinning ballerina, we're going to get a different measurement, v tag. And v tag will be a different velocity altogether, meaning it has both a different magnitude and a different direction. To be honest, we can forget about the stationary system for now. We know how to measure in a stationary system. What I care about now is the ballerina, the relative system. Just to reiterate, v is what's measured from the laboratory, and v tag is what's measured by the ballerina. So in order to do a list of forces for v tag, what we first want to do is account for the sum of forces. These are the real forces. Those are the forces that we normally talk about, such as gravity or friction or something like that. And we're going to add to that two different fictitious forces in the case of a rotating system. First, the centrifugal force. We're going to first symbolize that with this F. And secondly, we're going to add the Coriolis force. Now, of course, each of these are vectors. And in the end, they have to equal a tag vector. And this a tag vector is the acceleration relative to the rotating observer, that is the ballerina. Now it's time to incorporate our centrifugal and Coriolis forces. So let's start with the centrifugal force. One note to make is that the centrifugal force and the Coriolis force have no relationship between each other. They're two separate forces with separate equations and no relationship one to the other. So starting with the centrifugal force, F, the F vector, equals m omega squared r hat. The first thing to note is that this omega, the angular velocity, is the angular velocity of our ballerina, of our observer, relative to the laboratory. Just to reiterate, omega is the angular velocity of the observer, the ballerina, relative to the inertial system, the laboratory. What this means is even if the triangle, our object being observed, has some sort of omega, that is a radial velocity, we're still not interested in that. What we're measuring is the radial velocity of the ballerina, of the observer. We're measuring the change in the angle theta, this angle theta. Now the next thing is r, which is the distance from the origin to the object being measured. It's coming from the origin to the object, and that's r, and it's in the direction of r hat, which of course is the continuation or the same direction as this line r. So what we have is omega squared r in the direction of r hat, and that's what this line represents. So this essentially solves for me what we're talking about when we talk about the centrifugal force. And usually we're going to use this formula. However, the fuller version is the lower formula here. Now, what really is going on here is these are equal, of course. And as soon as omega is on the xy plane, as we normally have it, and r is on the z plane, or on the z-axis, we end up getting these two equaling each other. In fact, you can even see that the magnitudes are the same. You have omega times omega, or omega squared, times r. So the magnitudes are the same as long as the angles work out the same, which they do if we're working with omega on the xy plane and r on the z-axis, then we're set. So moving on to the Coriolis force, it may seem confusing, but once you understand what each variable stands for, it's rather simple and we can incorporate it easily. So we have negative 2m omega cross v tag. So what is each of these? Negative 2m is negative 2 times the mass. Omega, as always, is the angular velocity of the observer relative to the inertial system, that is the laboratory, and we can actually get rid of this relative here. And v tag, because it has the tag, we know that we're talking about a relative velocity. So it is the velocity of the object being measured, in our case the triangle, relative to our relative observer, the ballerina. So let's look at the example of our problem here. We already have v tag symbolized here, and what we need to do is find omega. So according to the right-hand rule, we can see that omega should be coming towards us. So this is the omega vector. So now I need to perform a scalar multiplication between omega and v tag that is, excuse me. And I know based on the right-hand rule that because omega is going in a counterclockwise direction, that what I need is something that is perpendicular to v tag, and it's going to come towards us. So this is the result of omega cross v tag. However, over here we have negative 2, meaning that the actual result we'll use in our problem will be going the opposite direction. So in fact, this line here is going to be the result of our problem.